So, in the last lecture we have discussed about the importance of single molecule fluorescence or single molecule spectroscopy itself. Right. Many such cases where the ensemble average picture is not good enough to tell about the system exactly. So, in such case the single molecule spectroscopy are very much efficient to comment what is going on. So, if we are now convinced that single molecule spectroscopy is one of the important topic, right, to discuss, right, we have to proceed to the most important part of the single molecule spectroscopy. How is it possible to see a single molecule, right? It is not easy. So, let me point out few important parameters which should be improved to observe the fluorescence from a single molecule. So, here is my detectability of single molecule is a issue, right. And most importantly, right, I need to ensure that the signal, the photon, number of photon coming out from a single molecule should be more compared to the background signal. In other words, the background should be very, very low, right. So, the background signal should be extremely small, right. Let us say you have this sample cell and you want to take a single molecule inside this sample cell, right, and sample cell is filled with some solvent, right, is filled with some solvent and you have a single molecule inside this solvent cell, inside this sample cell. And what is your intention? Your intention is to see the fluorescence coming out of this sample cell, that is your intention. Whatever the fluorescence, you will going to measure this fluorescence. You will going to take this sample in your normal fluorimeter and then you will excite and then at the right angle geometry you will going to record, right. There could be several sources for this background. Let us say for example impurity. If you have some impurity present, right, and those impurity will also emit a broad emission, broad type of emission or scatter in that fluorescence wavelength region, right. Then because you only have one single molecule and impurity level, if it is more, if in this sample volume you have 10 impure molecule, right, because the concentration of the solvent is huge, right, because it is a pure solvent. So, in this case the impurity has to be very, very low, right. And in this particular case when you have only one molecule, then there should not be any impurity, otherwise this impurity may affect the detectability of the photons coming out of your desired fluoropore, the fluoropore under investigation, right. Second, let us say emission from the optical components when you excite, because in the fluorimeter you have several optical component with coatings and this and that, right, and they also sometimes emits little bit of different colors of light, right. So, that also has to be taken care, because you are going to detect the photons from a single molecule, right, remember that. Number 3 is scattered light. Right. So, if there is any scattered light, like you are doing this experiment in this room, you have covered, but the covering was not good enough. So, there is some leakage from this side, that side, this side. So, some scattered light will be there, that will going to destroy your measurement, because the number of photon coming out from a single molecule is really small, right. If some lights are coming from here and there, then you will not be able to measure, right. And number 4, I can think of all these different issues. Number 4 is the dark count of the detector, that I already mentioned, that the dark count of a detector is because of the thermal electrons, right. If that is at this level and the count or these photoelectrons originating from few photons which is coming from the single molecule is over here, then you won't be able to see, right, because of this high level of the dark count. So, you have to lower this dark count in a minimum or 0 value, then little bit will be visible, right. So, this is another issue. Now, you consider that you have a sophisticated instrumentation laboratory, sophisticated purification facility, so that impurity taken care, emission from the optical component taken care, scattered light taken care, and dark count of the detector is also taken care. But still you will not be able to detect this emission from this single molecule. The reason is the intrinsic Raman scattering of the solvent. So, this is most important thing. If someone will tell you or someone will ask you what is the Raman scattering of a particular solvent, we usually mention the strongest peak, right. So, the Raman shift for water is about 3400 wave number, right. I will get a peak over there, but if you really extend, because of the presence of several vibrational and rotational state, although the intensity are small, right, but still the Raman scattering could be present throughout this emission wavelength, right. And now, if you consider that how many solvent molecules are present inside this solvent cell and having a particular cross section of Raman scattering, if you calculate, then what you are going to see is that the Raman scattering cross section is much. Let me do such kind of a calculation over here. So, what I want to say is that even you take care of all these different problem, but because of this Raman scattering is represented like this way, like this, and your fluorescence will be somewhere here. So, you will not be able to see this fluorescence in presence of this Raman scattering. This fluorescence is coming from your molecule, right, that means your fluorophore. And this Raman scattering is coming from your solvent. This is important. Okay, let me give you one specific example, then this will be more clear. Let us say that I have taken one molecule, this is called rhodamine 6G, let me represent as R6G in some solvent. Let us take this solvent as ethylene glycol. If I have to represent this emission characteristic of this rhodamine 6G, what information I should give you? I should give you the information of this fluorescence quantum yield. So, let us say this phi f, let us assume that this is equal to 1. That means, the rate constant of this non-radiative pathway is 0, right. So, only the radiative pathway is available for such for this particular molecule rhodamine 6G, my assumption, right. Now, I will also tell you the one thing, that is the absorption cross section of this molecule is, that is my also assumption, the absorption cross section of this rhodamine 6G molecule is same to the molecular cross section, right. So, that means the number of photons which will excite this molecule, right, will be 100%, right. If there are incoming 100 photons, all 100 photons will be absorbed by this, right, and the fluorescence quantum yield is 1. So, there is no loss at all. Now, this Raman cross section of this ethylene glycol is 3 into 10 to the power minus 12 angstrom square. Okay. So, let me write here the emission intensity of single rhodamine 6G molecule should be equal to some number of ethylene glycol molecule Raman intensity. Now, can I find out this number? Can I find out this number? I said that the absorption cross section of rhodamine 6G is same as the molecular cross section of the rhodamine 6G, but here this Raman cross section of this ethylene glycol is really small, right. It means that if I know this absorption cross section or molecular cross section of this rhodamine 6G, right, then the number of molecule which will interact with rhodamine 6G, right, that I will get an idea about that how many such kind of photons is actually going incoming, right, incoming photon is actually going to create my Raman intensity, right. So, if the rhodamine 6G molecular cross section is, let us say, 4 angstrom square, it means that emission intensity of single rhodamine 6G should be equal to this 4 divided by this, right. So, here should be 4 divided by 3 into 10 to the power minus 12. Now, this is number, right. So, this many molecules of ethylene glycol, because here for the Raman cross section is really tiny, 10 to the power minus 12 angstrom square, right. So, emission intensity from one rhodamine 6G molecule should be equal to 1.33 into 10 to the power 12, right, ethylene glycol. Let me write as Eg, ethylene glycol molecule Raman intensity. That is for sure, right. That means, the one number of photon coming out of a single rhodamine 6G molecule means is equal to the Raman scattering, or those photons of the inelastic scattering of the similar wavelength, let us say, of 1.33 into 10 to the power 12 number of ethylene glycol molecule, they are same, right. So, now I will take one condition, that is our ensemble average condition. Usually we prepare a solution of micromolar, right. So, let me take this condition that for the ensemble experiment, you have, let us say, 1 ml of 10 micromolar rhodamine 6G in ethylene glycol. This is my system, right. So, your system is this, right. So, I can readily calculate how many rhodamine 6G molecules are present, how many ethylene glycol molecules are present, right, in this system. So, let me write one by one. So, Avogadro number, ten micromolar and 1 ml 10 to the power minus 3, right. This equal to 6.023 into 10 to the power 15, right, R6G molecules, right, are present in the system. How many number of ethylene glycol? So, I know this 1 mole of ethylene glycol is equal to 56 ml of ethylene glycol, that I know. So, 1 ml ethylene glycol is equal to just simply this 17.8 millimole of ethylene glycol, right. So, this equal to 17.8 to 10 to the power minus 3 to 6.023 10 to the power minus, no, not minus 23 Eg molecules. If you do that, this will be equal to 1.07 to 10 to the power 22 Eg molecules in the molecules are present in the system. Look at these two number, one is this one. So, I will just highlight this, one is this one. So, this many of rhodamine 6G molecules are present in the system and this many of ethylene glycol molecules are present in the system. What is your system? Your system is this one. So, this is your system, right. Now, if I consider that one rhodamine 6G molecule, right, will the fluorescence quantum yield is 1, that is I have already assumed. So, will give 1 photon, right, or 1 emission intensity, unity emission intensity, right. So, 6.023 10 to the power 15 rhodamine 6G will give the emission intensity. So, now I will write a intensity, right, coming out of rhodamine 6G will be 6.023 to 10 to the power 15. Now, the intensity from Eg, right, that I should calculate here. So, in this case I have this number 1.07 10 to the power 22 Eg molecules are present. So, 1.07 to 10 to the power 22 molecules are present, and I have seen in my previous, see here, emission intensity of single rhodamine 6G molecule means 1.33 to 10 to the power 12 Eg molecule, right. So, I should divide this number by this number 1.33 10 to the power 12, that means it will be comparable to 1 rhodamine 6G molecule, right. So, this divided by 1.33 into 10 to the power 12. So, then this will going to be 0.8 into 10 to the power 10. So, as you can see here, if this is the intensity of emission from the rhodamine 6G, which is 10 to the power 15, and the intensity of Raman scattering from this ethylene glycol is 10 to the power 10, which is much smaller, right, compared to this intensity of rhodamine 6G. Now, if I consider the for such a case in this system, right, that is 10 micromolar rhodamine 6G in ethylene glycol, and I have taken 1 ml of such solution, then I can simply convert this as, I can write this as 1. So, this emission intensity will be roughly, right, roughly 10 to the power of minus 6, 10 to the power minus 6. So, this intensity is because of the fluorescence, and this is because of the Raman scattering. So, which is negligible? This is 1, this is 10 to the power minus 6. So, this is negligible. Now, my interest is not this ensemble average picture. My interest is 1 rhodamine 6G molecule, that is what I was discussing here, right. 1 rhodamine 6G I have taken in 1 ml solution. So, next I will change my system to the single molecular level. Now, my system is 1 rhodamine 6G molecule in 1 ml of ethylene glycol, right. So, now this is my system. So, 1 rhodamine 6G molecule will going to give you 1 intensity, right. So, if I now write this intensity, rhodamine 6G, what I am going to get is just 1 over here, and the intensity of Raman scattering by this ethylene glycol, that depends on the how many ethylene glycol molecules are present. That number I already have determined over here. So, 1.07 10 to the power 22, right. So, in this case the intensity of this scattering will be 1.07 to 10 to the power 22, and this cross section, right, that number which I have already calculated, 1 rhodamine 6G is proportional to this much. So, I have to divide this with 1.33 into 10 to the power 12. Basically, this number is same, and it has to be equal to same because it depends on the how much ethylene glycol you have taken. In this case 1 ml, in this case also 1 ml, but here you had taken 1 micromolar solution of rhodamine 6G. So, number of rhodamine 6G molecule was very large, right, 10 to the power 15, but here is only 1. So, here that Raman scattering is 0.8 into 10 to the power 10. Now, you see this is 10 to the power 10 and this is 1. So, fluorescence intensity is negligible in compared to the Raman scattering. So, here Raman scattering much more than the fluorescence. Let me take my third system as one rhodamine 6G molecule in 100 femtoliter of ethylene glycol. Right. If it is 100 femtoliter, so then intensity R6G, this is 1 because I have only 1, and here ethylene glycol, then this number will change. So, in this case the number is 17.8 into, because I have 1 femtoliter, right. So, it is 17.8 into 10 to the power minus 13, right, into Avogadro number. So, it should be proportional to this. So, then this will be into Avogadro number, means this will be 1.07 into 10 to the power 12 molecules of Eg. Then I will divide this by 1.33 into 10 to the power 12, right. So, then this will going to be intensity. Now, this no longer be molecule. So, then this will going to be intensity of Raman scattering. So, this is going to be 0.8, right. So, you see here for such case, when one rhodamine 6, note here, one rhodamine 6G molecule in 100 femtoliter of ethylene glycol, I got the fluorescence is 1, I got the Raman is 0.8, right. So, this is the catch. So, for the ensemble I had one fluorescence 10 to the power minus 6 Raman, so no problem. But when I took one rhodamine 6G in 1 ml ethylene glycol, what I got, one fluorescence means 10 to the power 10 Raman, and it is problematic, right. You cannot see 10 to the power 1 fluorescence in front of 10 to the power 10 Raman. But when you have taken one rhodamine 6G in 100 femtoliter of Eg, you see the emission intensity is 1. So, this is your emission intensity, and 0.8 is your Raman scattering. Now, if you further decrease from 100 femtoliter to 1 femtoliter, then this value will be 0.008, right, 0.008. So, if you further decrease the volume of the sample, that means my next system, and which is my system for future studies, is 1 R6G molecule in 1 femtoliter of ethylene glycol. In this case, intensity R6G, fluorescence, and Eg Raman will be, if it is 1, then it will be roughly 0.01. So, this is a good situation for me to monitor the fluorescence intensity coming out from a single rhodamine 6G molecule. So, the catch here is I have to confine this one rhodamine 6G molecule in 1 femtoliter. It is not 1 ml, it is a very, very tiny volume. So, that is the catch, and if you can achieve it, you will be able to see the single molecule as I have described till now. And in the next class, what I am going to do, I am going to show you how to achieve such kind of small observation volume. And this is the key, right? If you cannot achieve such kind of small observation volume, you won't be able to see the fluorescence from a single molecule. So, let me finish here and we will continue our discussion on the next day. Thank you very much.